Uh, Good morning to all. Thank you very much, Panda sir. So, for last couple of days, we discussed about some basic fundamental things which are required to know the transport properties in low-dimensional structures that may be either in quantum wave, quantum dot, quantum wire, etc. So today I basically discuss with you the some research related uh, uh, topic, uh, particularly the electron mobility, which is an important parameter as all of you know, because the conductivity J, so which can be improved if we improve the mobility. So some different types of quantum structures and how we can modulate the mobility with respect to the structure. So that we will discuss. So I hope all of you will enjoy. So if you have any query, you are all free to ask. So let's start from our previous lecture that already I have stated the carrier transport phenomena. As all of you know, in our school level, in plus 2 or plus 3 or graduation level, master's level. So specifically, individually, the electron, if we take, this is a silicon crystal, so there are crystalline structure, so periodic arrangement of atoms. So the motion of a electron in a crystal is very fast. If you see that motion is of the order of 10 to the power 7 centimeter per second, the velocity of the carrier in a crystal is 10 to the power 7, that is centimeter per second. However, as there are 10 to the power 18 per cubic centimeter, number of atoms are there, so they have scattering or that means they have random motion, and due to their random motion, if one electron is moving in this direction, in one direction, there must be another electron in the opposite, that is in this direction, the fourth direction. So due to this, or we say this one electron is moving in this direction, now there may be a collision, okay, then move in second line, then it can again make a collision, it can move in the third line, and ultimately maybe there is another collision, so it can scatter into again to the original position. So due to this randomness, random property of these carriers inside the crystal, so if you are not applying any electric field, then the net displacement is zero, so we say the current density is zero. So that's why we are applying electric field or magnetic field, or we can increase the temperature, or you can make a concentration gradient. There are different techniques through which we can get the current in a crystal, current density. So specifically, which is equal to NEV, that is the drift velocity, or sigma into E. That sigma conductivity, which is Ne mu plus that is Ne mu E plus mu H, the mobility, combination of mobility of electron and hole. If we consider only a conduction band, then there is no hole, only the electron. If you are taking a bulk semiconductor, you can get both electron as well as hole. Or this here mobility, which is E tau by m star, that tau is very important, which here today we will calculate this tau. So if you see very interesting fact here, so the conductivity depends upon n, that is number of concentration, the dope, number of dopants, as well as it depends upon the mobility. But if the number of carrier concentration is more, there is a chance they can scatter a lot, they can make collision, more scattering, that can reduce the mobility. So that is the technique. That means how we can design a structure so that although we can add more and more concentration, if you add the doping concentration, but you should design the structure in such a manner that your mobility should increase. That is the technique or research that you can carry out. So that part today we will discuss about this. So this is basically, so as you know, the mobility, which is an important material parameter, because mobility is more in case of a material, then that can give rise to higher conductivity, that also improves the speed of the operation of the device. So in actual material, actually there are different types of impurities, defects. These defects and impurities may be during the growth process, because although we are adapting clean room, however, we can get some impurities or defects, and also to increase the mobility, we are intentionally adding impurities. So that can give rise to different types of scattering, which can limit the mobility. So how we can design the structure in such a that although we add impurity, however, it can reduce the scattering, improves the mobility. That is the main aim. This is important when we take T equal to 0, that means our 4K, that is at low temperature operation. But at room temperature, as you know, at room temperature, the lattice, that means if you take a crystal, this lattice, each atom in the lattice, they will vibrate. And once there is vibration, once there is vibration, then it can generate the scattering, which is called lattice scattering, that is by collision between electrons and phonons. So that vibration generates phonons. That phonon can interact with the electrons, which will give you the lattice scattering, or we say also phonon scattering, and that can reduce the mobility. So phonon scattering is the dominant one when we take high temperature, and at low temperature these impurities, defects, or alloy or interface roughness, they can contribute. That means they can dominate the mobility. So this is all about what we have discussed in the first lecture. So this scattering, specifically, where we will get scattering. That scattering may be intravalley, may be inter, or maybe interband or intraband. So there are multiple choice. What does it mean? Let the structure A here. Suppose the position of the electron is at k position. The vector k value is k. So it faces an collision or scattering, and due to scattering, it changes its position from k to k prime. So as the electron, due to scattering, the initial position is k, and the initial wave vector of incident electron is k, and the k prime, which is wave vector of the scattered electron, and it is occur in the same valley of a bulk semiconductor in the conduction band. So we can say this scattering is intravalley. Similarly, if such scattering occurs in the valency band, then we will say this is the intravalley scattering in the valency band, or here it is in conduction band. So there may be also intervalley scattering of electron, just like I have shown last class. If you take a gallium arsenide, so when you apply electric field, as electric field increases, that electron can jump from gamma valley to L valley. So that means when the electron scattered from one valley to other, then that scattering, we say it is intervalley scattering of electron in conduction band. Now there is chance the scattering may be interband scattering. Interband in the sense, let here we take a valency band. So in valency band, as per our discussion from last class, so there may be a heavy hole and a light hole. That heavy hole and a light hole band. So there is a chance the hole present in this position, in the light hole, that may face a scattering, and that can finally move to the heavy hole band. So in this case, we say it is that means interband scattering. Sir, my voice is clearly audible.
Yes, sir. Yes, sir.
Okay. So normally we classify the scattering in different depending upon their conservation in momentum and energy. So as for the basics that we you know from your intermediate or graduation, if in case of a scattering there is conservation of that energy or momentum, we say this is elastic scattering. If that momentum or energy is not conserved, we say it is inelastic scattering. Specifically, which ionized impedance scattering, piezoelectric, surface roughness, alloy scattering, etc. These are the elastic, whereas specifically the phonon scattering, that is lattice scattering, phonon that may be optical phonon or acoustic phonon. So also there may be electron-electron interaction or deformation scattering. So such scattering phenomena, they are known as the inelastic scattering, and these were known as the elastic scattering, which there is conservation of energy and momentum. So specifically in today's lecture, I will focus on this ionized impurity, surface roughness, and alloy scattering, because whatever what we are studied the scattering, the transport, that is mobility. We study mobility for low temperature, and normally at a low temperature, these impurity, ionized impurity, surface roughness, and alloy scattering, they can contribute, or these are the deciding factor which decide the mobility. So here I have shown only for your clarification. See, there is a positive ion, very heavy ion at this position. The electron, which is headed towards the, due to the motion, the electron headed in k direction, that is the incident direction of the wave vector in the k direction. Now, as there is a positive ion, so that is a heavy ion. So that means that electron, it will make a scatter. That means instead of moving straight, now it changes the direction. And now the final wave vector direction is k prime with velocity k prime. Initially, it is moving in the k vector direction with velocity pk. After scattering, it will be moving in this direction. So what is that elastic? So as we say, so you can see here. So let this is the initial state. So now due to this collision scattering, it is take the direction this k plus q in this direction. Then as for the elastic phenomena, elastic scattering phenomena, this wave vector, incident wave vector k, if we say take it k space, the k modulus should be equal to that of k plus q modulus. If this satisfied, then if we represent it in a circle, that scattered circle, then this should be satisfied. Then we say it is elastic. So regarding surface roughness, as all of you know, basically it is common in Moss structure because it is common in Moss structure because the oxide, which are having different different A, that is lattice constant, and silicon, which is of different lattice, that is two different material. So semiconductor silicon and SiO2 is a insulating material. So at the interface between SiO2 and silicon, the surface is very rough. As the surface is rough, when that can reduce the mobility. So we will discuss in detail with mathematical expression. Alloy means when you are forming a tertiary or quaternary compound semiconductor, when you add alloy, that is the aluminum concentration or indium concentration, then that can replace the lattice with other atoms, atoms. So it will give you the alloy scattering that we will discuss in details further. So see for phonon, if you say this phonon scattering, that means the phonon is obtained due to lattice vibration. That means when temperature increases, so that means when temperature increases, the lattice can vibrate, and during the vibration, that can it can give rise to scattering, which can reduce the mobility. So you can see uh, electron-phonon interaction that is under different categories, such as either maybe it is known as the acoustic phonon or optical phonon that we will discuss, or due to the polarization, that means if the particular material is polarized due to the asymmetry nature of the crystal, if there is polarized, it can also give you scattering. These are two types, transverse and longitudinal scattering. And there are other different mechanisms which is also gives rise to electron-phonon interaction at high temperature, like deformation potential, polar scattering, piezoelectric scattering, etc. So during this scattering process between electrons and phonons, both wave vector and energy are conserved to lowest order in the contribution theory. That means if you see, let this there is a incident electron having momentum vector k, that is in the k vector having energy k. So due to this scattering, let there is a photon. So due to this scattering, now it is the final direction of the energy. The k position is k prime and energy ek prime. So now k prime, which is equal to k plus q, and ek prime equal to ek plus h plus omega q. This additional factor, that means here it absorb that photon. So here there is absorption occur, and same time there may be emission in this electron-phonon interaction. You can see here the final energy Ek prime, that may be Ek minus h plus omega q, where a phonon which is emitted due to this scattering phenomenon. So this scattering, particularly the phonon scattering, is classified into the optical phonon and acoustic phonon. So this is the general basic. I hope all of you know. So this is shown in first brilliant zone from pi by 8 to pi minus pi by 8 in the k direction. So see, if you that means these are the initially it is plane, that is like a line. So when temperature increases, now these are the atoms. These are two different atoms having mass m1 and m2. So and let the lattice is A is the lattice constant. So now when temperature increases, now this lattice vibrates like this. As the lattice vibrates, so in some case that the two due to this vibration, that may be headed in opposite direction like this black one and green one, gray and green one, or they headed in the same direction like this in the lower one. So this last one, which is the acoustic, and this one is optical. Normally optical phonon scattering occur at high frequency, omega versus k. So normally it occur at a high frequency, which is peak at the center of the brilliant zone, that is 0, and it gradually reduces towards the edge of the brilliant zone. Whereas in case of acoustic, at center it is a quite 0, and it enhances towards the both sides of the brilliant zone. So this phenomena, that phenomena can be expressed in terms of we say this is the dispersion relation, that omega square plus or minus this. So where this k, that means it seems like a spring. Let us we take consider it as a spring. If it is a spring, then we say it has a constant like spring constant. The spring constant is capital K, and it is shown in 1D. So 1D alternating array of two types of ion or atoms of mass M1 and M2 that repeated periodically at a distance A, and we take springs of spring constant K, then we can see two modes of vibration, that optical and acoustic. So when the sign is positive here, either plus or minus sign. So when sign is plus, in dispersion relation, if the sign here is plus, then we say that is a optical mode, And if the sign is minus, then we say it is the acoustic mode. So here this k is the wave vector of the vibration which is related to wavelength, that is 2 pi by lambda. So in the optical mode, actually, there are two adjacent different atoms. They move against each other. That I have shown you here. The two atoms, they move against to each other. Whereas in case of acoustic, the two atoms, they move in the same directions. So here I have shown this different this phonon, optical and acoustic phonon generated. This is in case of gallium arsenide. So or some wave that so here if you see this one, the blue one, which is the acoustic phonon, because it is originate from the origin at gamma value, it starts with 0, then it is enhances and towards the L value on both sides, this. So however the upward two, these are the your optical phonon scattering. So specifically, this is important when you consider the device or your calculation for a high temperature. So then go for the that already is this one is important one that we have discussed, the inter-subband scattering. So as you know, the inter-subband scattering, say this is a quantum wave. So these are the discretized energy levels E0, E1, E2. These are the discretized energy levels. So let this red one is the Fermi level. As the red one is Fermi level, so the states which are below the Fermi level, they can contribute for the conduction process. That means the electron which are present below this Fermi level, they can contribute for the conduction process. So let's see if we take a cross section of this parabolic approximation. So if we take a cross section, the above one, see you can see the electron due to the scattering phenomena that can come from 1k, from 0k to 1k, or 0k to 0k prime, or 1k to 1k prime. That means if the electron due to scattering, it moves from 0k to 0k prime. 0 means like initial state we say take 0, final state is 1. K is the position, initial position, and this k prime is the final position. So here it moves from 0k to 0k prime. That means both is in the same energy level. So we say this is intra-band transition. This transition is called intra-band, intra-band and intra-subband. Sorry, this one is called the intra-subband because this is conduction band. If you take a lower one is the valency band, so then we say this is one and this is another band. If there is transition from conduction to valency, we say interband. If there is a transition from E2 to E0, that means in the same band, we say it is interband. Again, we make it subband. E0 is one subband, this one is one subband, this one is one subband. If there is a transition from 0k to 0k prime, we say it is intra-subband. If there is a transition from 0k to 1k, or then we say it is the inter-subband scattering. And this inter-subband scattering is an important parameter which decides the electron mobility. It play an important role on electron mobility. That means when there are multiple number of subbands occupied, like suppose E0, E1, E2 like this, when there are multiple number of subbands, there is a chance the electron can move from this EF, this to this. That means here, if the electron present here, okay. So see, if the electron present here, that means in E0 in this value. Now from E0 it come to E2 or E0 to E1. That means there are multiple number of energy levels occupied. So in this case, the intra-subband, there is a chance it can move from this EF. That means from this position to this. That means intra as well as inter. So in case of multi-subband occupancy, both intra-subband as well as inter-subband, both will take part in the take into account for calculation of the mobility. So how we will proceed? So the electron, that means when if you see when an electron present inside a well, in this well, so it is satisfied the, that means we can find out when an electron is inside the well, that means we can find out its energy, and energy is nothing but the eigenstates and the associated or corresponding wave functions. These wave functions, which is your the, that means the eigenvalues. So to calculate the eigenstates and eigenvalues, that means as for this, the electron subband energy level and wave function of the quantum well structure, we can say this ENK, because there are number of energy levels, either 1, 2, 3 like this. So ENK is equal to the EN, the minimum conduction band energy, EN plus h cross square k square by 2n star, that is the effective mass. Similarly, that electron which is present in the energy level ENK, it is associated with the wave function which is psi nk. The R is two-dimensional vector equal to the power I k rho by root over of a psi nj. So here, if you that means to find out your aim is to find out the solution, that means to find out the energy and its associated wave function, then you will go for this solution of this Schrödinger's equation, because it describes the wave characteristics in a quantum mode. So that is minus s cross square by 2m d square by dz square plus dz psi n equal to En psi n. This En is the energy level, energy states, and the associated function is the psi n. So here that V, which is the potential, if you see here, this is a only a square potential wave. That means when we say this is 0 to L, when outside the well it has a finite height, inside the well it has a height is 0. So we can say the potential is 0. So this one is known as the structural potential. You can take structural potential, but when you dope, that we have seen in last class, for example, you make a modulation doping. So when you dope, then there is band bending, which is obtained by solving the Poisson's equation known as the Hartree potential, VH of J. Now, in addition to this, suppose you want to apply the contributions, that may be electric field, magnetic field, etc. So depending upon the field, you can get an additional potential, which is called the VFJ. Here I apply the electric field, so I say it is V of Z. Therefore, the total potential is the sum of structure potential, Hartree potential, and potential due to application of electric field. So now, so actually the Schrödinger's and Poisson's equation, it needs to be solved self-consistently, because simultaneously our aim is to find out the energy level, wave function, as well as the number of occupation, that means the energy, how many number of energy levels occupied. So it needs to solve self-consistently. However, for simplicity, that we adopt here, we obtained an expression of Hartree potential by solving Poisson's equation, using we take a trial wave function and we adopt the variational approach. Here we adopt multi-step potential approximation to calculate the transmission coefficient for the potential profile and obtain the subband wave function and energy level, that is IN and EN numerically. You can see here. So any potential, take a let us, this is arbitrary potential. So you just divide this whole potential into small parts. So now you solve for each, now each one is act like a barrier. So if you solve, then for the transmission coefficient, that means let a energy, electron having energy moving in this direction, so in the towards the barrier. So if you solve this one, then you can get the transmission coefficient, and you put the boundary condition. That means there must be continuity of psi j. That means the psi j, the wave function, the psi j, that continuity will be taken at the boundary, on both the boundary, and also as we take a, this is a, barrier, so the Bn plus 1, that means this A0, must be equal to 1 because it is incidented energy, and the Bn plus 1 as uh, uh, towards the right side, there is no chance of this. So this Bn plus 1 should be equal to 0. Now equate an plus 1 into 0, that and you solve, because aj and bj, these are the incident energy from the left side, mi, that means if you go for the exact mathematics, you get a that matrix, incident this mi matrix, and you solve, you can get the energy levels. So uh, as I already told, to get the Hattie potential, you need to solve the that is the Poisson's equation. So for Poisson's equation, as you know, this is equal to this 4 pi square by epsilon 0, because this is in CGS unit, that into the charge density. So here the charge density, which is ND of Z minus N of Z, that means that ND of Z depends upon our doping, how much concentration we dope, how much electron, how much dopant we dope. So it depends upon the doping concentration, and N of Z, which is the electron concentration, and that electron concentration is equal to the summation over nn psi n z square. This nn is the number of states occupied. So in our case, we are calculating the mobility at low temperature. So the temperature equal to 0 K. As T equal to 0, and we also assume whatever the dopant we dope, all the dopant get diffused into the well. So the Ns, that is the surface electron density, is equal to N0 into 2D. 2D means if we dope symmetrically on both sides of the barrier. I will show it. So that Ns, which is a equal to the expression of that Ns, which is m by pi square Ef minus En theta Ef minus En. That theta is Heaviside step function, and due to that t equal to 0 K, it became Heaviside step function. Otherwise, we got the expression that I have explained yesterday. So now, if you take a suppose a structure having not symmetric doping, that means if you dope, suppose this is ND1 and ND2, two different doping, then in this case, so your doping profile will be different. So you take your doping profile accordingly, and you also get the NS, which in previous case, the NS is equal to N0 into 2D. However, here this NS should be equal to ND1 plus ND2 into D1. Let this thickness of doping is D1 and this side is D2. So how you can calculate the mobility? So normally we calculate mobility by using Matheson's relation. That Matheson's relations means, see, if we are considering different types of scattering mechanism like ionized alloy interface that I have explained already. So here due to each individual scattering, you can get a mobility. So you find the mobility due to impurity, alloy disorder, interface roughness, and you take the Matheson's relation. That means 1 by mu is equal to summation over S 1 by mu S. That means 1 by mu equal to 1 by mu IL plus 1 by mu L plus 1 by mu IR. So by using this, we can obtain the total mobility due to in a system. So that mu S, which is due to mobility due to scattering mechanism, which is equal to this summation over nn mu n s by summation over n. That nn is the number of states occupied, and this mu n s, which is that means mobility due to nth subband. So if you solve the BT, that is Boltzmann transport equation, I will show you. So you will get the mobility, which is a function of Fermi level, because at t equal to 0, the electrons which are present over the Fermi function, Fermi surface, that they will contribute for the mobility. That's why that mobility is a function of Fermi function. So this equal to E by n star tau n of S. That means this tau n, which is subband transport lifetime for scattering mechanism, and that can obtain by using BT. So For each individual scattering, you calculate mu n of s by calculating tau n of s. That tau n you will calculate by using Vt. Then use mu n of s, you calculate what is mu s, that is mobility due to a individual scattering. Then use this mu of s, then you calculate the total mobility. That is the flow, how we can calculate the mobility. Now, that electron mobility that can be calculated by considering different strategies, already I told. So, which is by solving the PT Boltzmann transport equation. So, if you see, there is a electron which is at initial position nk n, that means at initial position k with the n subband. That means that a electron before scattering, initially it is at position k position with the at subband n subband. Now due to scattering mechanism, let the final position of that electron is k prime, that and at a subband n. That means it is due to scattering, it moves from n subband to n subband, from k position to k prime. So then in this case, this the Boltzmann equation shows that the relaxation time approximation, that means the distribution function phi n is correlated with the that transition rate, that W is transition rate. So this equation, if you take further simplification, you see this one is known as the Fermi-Golden's rule, which is a very important one for transition of electrons of for this due to this scattering can be obtained by using Fermi-Golden rule. So this Fn0, that Fn can be obtained the distribution function as this, where this Fn0 which is the Fermi direct distribution function, this Fn0, this tau n which is the subband transport lifetime, this W as I explained, this is the transition rate from k prime position, sorry, not k prime position, sorry, this is k to k prime position, that is from subband n to m. And this Vt, that is Boltzmann transport equation, this can be reduced to a coupled linear equation about this tau n. And at t equal to 0, only the electron on the Fermi surface, they contribute to electron transport. That means if you take t not equal to 0, this simplification may be a little bit complex, but if you take the temperature equal to 0K, because you know in your Fermi Dirac distribution that Fn is a function, F is a function of energy, Fermi level, and T temperature. But if you take temperature 0, then that became very simplified, which is became Fn0K. That means the Fermi Dirac function at T equal to 0. That's why this is called Fn0. So how can solve that Vt Boltzmann transport equation? So in simply this that can be expressed as, this expression can be expressed as, if you go for little bit calculation, summation over j equal to 1, aij tau j equal to 1. What is that tau j? That is the transport scattering rate, that is transport time. So here, this if there is only single subband, as already I explained, single subband means let only E0 is occupied. That means the below Fermi level there is only E0. If this is only, that means j equal to 1, only a single subband. If j equal to 1, here I say 0. That means for lowest orbit, lowest subband, I say it is E0. That's why I notate here 0. So if you see, if j is 0, only single, then that expression became 1 by tau 0, we can express as V0. But if it is a double subband, that means j equal to 0 as well as 1. That means there are two levels occupied. Below Fermi level, there are 0th and 1th level. That means the two levels are there. So if j is equal to 0 and 1, so now this is j equal to here equal to 1. Actually this value 1 to n. That means n equal to 2. So you can take j two values and you can change I. if you change I 0, 1, 2, 3 like this, if you change I, then you can see and you go for the solution, you will see this expression is equivalent to, we can get 1 by tau 0 and 1 by tau 1, which is expressed as here. That means that tau 0 can be expressed, tau 0 and tau 1 can be expressed in terms of B, C, D. So these are the scattering rate matrix elements. So here, if it is B00, that means there is a transition from 0th subband to 0th subband. So it is intra subband transition. So we say B00, this one is intra subband scattering rate matrix, B00. However, this B11, C10, D01, etc. The B11, this B11, 1 to 1, so it is also intra subband. However, if it is 0 to 1 or 1 to 0, it is inter subband. So, for a multi subband system, that tau j that contains intra subband scattering rate matrix elements, that is BNN, either B00 or B11, as well as it includes the inter subband scattering rate matrix element like C01, D01, C10, D10. So this is very simple. If you go for the simplification of this expression, you can get it. You can get this. So this B, C, D, the mathematical expression notation for this, it depends upon the scattering angle. So theta is scattering angle, and it depends upon the screened scattering potential. So B, C, D, that can be expressed in terms of the scattering angle as well as in terms of the mode of the square of the scattering potential. So we will find out this potential in the next slide. So here, that means for BMN, it depends upon the integration 0 to pi d theta 1 minus cos theta. That means it is a function of 1 minus cos theta. However, C is a function of only d theta. That means it will be integrated over theta from 0 to pi. However, for D, this is a function of cos theta. So that difference in the expression, the cosine function, leads to different scattering scattering values, scattering matrix elements values due to this. So this probably we take it is symmetric in nature. That means the CMN is equal to CNM. That means C01 is equal to C10. Similarly, D01 equal to D10. So that C and D are considered as symmetric in nature. And here this Q, the Q is after transition, you get the Q n to L, which is expressed in terms of this K, KFN square plus KFL square minus 2KFN KFL into cos theta to the power half. What is that KFN? Which is equal, depends upon the EFN, that is the Fermi energy level. For example, the Fermi energy level from 0 to 1. So F0, that means EF minus E0. If it is EF1, that means Fermi level EF minus the energy level E1. So that you can get the KFN. So now this is about the basic calculation, how we can calculate it. As I explained, you proceed from the Fermi golden rules. That means use BT, Boltzmann transport equation, and you further simplify it. And at t equal to 0, you can get the expression of tau 0, because for mobility, as I explained, for mobility, our aim is to calculate the tau. If you calculate tau, you can calculate the mobility. So from simplification of the BT, you can now get the expression of tau 0 and tau 1. Now already I explained the different scattering mechanism. So let it be again analyzed in details. So that ionizing impurity. So that ionizing impurity scattering is obtained due to ionized donors or acceptors or substitutional impurities. That means if you substitute some impurity in a material or due to charged surface states, that will give you the impurity scattering. So as impurity scattering is that means it is elastic scattering. So there must be the energy or momentum should be conserved. So if you say this in the K space, that means there is a initial direction is ln K, and due to scattering, it is scattered at an angle theta, then now it became in the k plus q direction. So as it is k plus q direction, so that means for conservation, the k plus q modulus should be equal to k mod. And if you go for the, if you take a this angle is theta and y vector is q, and if you go for this elementary geometry, because we take it is a vector line, a circle in k space, take a circle in k space. So if you go for the simple mathematics, mathematical geometry, then you will find that q is nothing but 2k sine theta by 2. So uh, so for ionized, so this one that there is a, as I explained, there is a heavy ions, positive ions. Now the electron, so due to these ions, it get scattered with a distance, let the electron which is at a distance r. So if the electron is at a distance r, then the potential due to a single ionized impurity with net charge, the charge of the electron is z into e. Z is the atomic number. So in simple, it is equal to Vi equal to as per Coulomb relation, Z is square by 4 pi epsilon r. So in the one electron picture, the actual potential seen by electron is screened by the other electron in the system. But when you take a crystal, that means there are not a single electron. There are other electron also present. So when one electron is interacting with the positive ions or another impurity, now there are other electron present. They can screen the effect. They can modify this interaction, Coulomb interaction. This phenomenon is known as the screening, which is very important one when we go for multi-electron phenomena. That means we consider there are large number of electrons, that is 10 to the power 11 order per cm square. So there will be screening. So what is screening? I will explain later on screening. So let first the alloy digital scattering. So as you know, digital scattering, which is calculated by using either VCA, that is virtual crystal approximation, or coherent potential approximation, and it limits mobility of ternary and quaternary compounds, particularly at low temperature. For example, you are taking gas. If you are taking gas and a gas, then you can in the aluminum gallium arsenide, due to the presence of alloy, it can. So there are different. So, for example, you take a material in which this part is all gas and this part is gas. So here in all gas there is alloy concentration X. So you can get alloy scattering in the barrier here. So this part is gas. But there are other compounds or other structures where you can get also, that means that scattering in the OL itself. For example, if you take here the electron gas is essentially localized in the binary material. The electron is localized here in the binary material, and faintly experience the alloy scattering in the ternary barrier. Here there is alloy, so that electron it very rarely interact with this alloy scattering. However, you can take some other example. For example, if you take the electron gas which are essentially localized in the ternary alloy and weakly penetrate the barrier. If you take, for example, indium phosphide and gallium indium arsenide, then in that means indium phosphide, over indium phosphide you will grow, then this barrier which will be indium phosphide. So you take the oil which is gallium indium arsenide, where you get alloy. So here electron is confined, the electron is here, and it can somehow also interact with the barrier that alloy is scattering. So this VCA, which is originate from the tight binding methods and replace atoms with effective mass. So here you choose parameterization to return alloy properties. That means any zero potential which is generated can be used to this the energy of the average energy is equal to 1 minus x energy of a material plus x into that average energy of b. P. That means this X is the alloy concentration. If you take alloy gas, the aluminum concentration is X. It changes due to the scattering from nth position to let n prime. So here, that means, for example, in your alloy gas, so one of the constituent atom like arsenic that may occupy the sides of the FCC of the gene blend structure. That means it can replace the gallium or alloy. It can take the occupy the position of gallium or alloy. So in this case, that can give you the this specific alloy scattering. So similarly, in case of the interface, as you know, this is very important one in case of your MOS technology. So this is a short range interaction due to the fluctuation of heterojunction or oxide semiconductor interface. You can see here, this lower one is the semiconductor, the upper one is the oxide. If you this is the if you see regarding the interface, so how the interface is not properly matched, there is mismatch in the interface. As there is mismatch in the interface, if you see here, now see, now these are periodic arrangement. Up to this is periodic arrangement. Now above this, due to this oxide, so there are two other atoms which are not in periodic order. This leads to the scattering, and which is known as the interface roughness. So the roughness, that means it arises due to mismatch in the that lattice constant as well as during the growth process. If your growth process is not fine, then you may also get a rupture at the interface. So that limit the mobility in MOS devices, specifically at a high effective surface fields. So we can model this IR scattering potential. We can model this by this, where V0 is the height, potential height at the barrier. Take the Z is the position, and due to this interface roughness, there is a random function that describes the deviation from an atomically flat surface. That means from the flat surface, let there is a deviation delta R. So this H is the potential. So that potential can be obtained due to this IR scattering. The barrier height into that theta function minus Z plus delta minus V0 theta minus Z. That means that can be expressed as V0 delta of Z into delta R. So you can see, if you zoom it, then that surface will look like this. Instead of flat, there will be roughness. So as there is roughness, when our electron is confined in this OL, if we say this is a OL and this is a barrier in terms of quantum OL. So as the OL is a finite OL, so some of the electron can penetrate into the barrier, because there is a chance we can get some electron concentration in the barrier. So when that electron move into the barrier, so when you apply the block function, now that block function is not symmetric here due to this interface. So this is a very crucial, it plays a crucial role for mobility. So you can see there is a see on the high resolution P10, that is transmission electron microscopy. You see, we can model this IR. That extensive experimental studies have led to two commonly used forms for the optocovariance function. That means that from the flat band, from the flat surface to this deviation, that from an flat surface, that deviation can express in terms of a optocovariance function. So normally the power spectrum of the optocovariance function is found to be either a Gaussian or exponential. So normally in our analysis, we assume that optocovariance function is a Gaussian function, which is in the form by this one. So where this delta, which is the RMS root mean square value of the roughness, and that zeta, which is the roughness correlation length. So if you see here, so this is here in Gaussian model, this that means let that interface, at the interface, it is in Gaussian nature. Roughness is estimated as Gaussian nature. Then it's roughness correlation length is different in case of exponential model. So specifically in our analysis here, we take this Gaussian approximation. So it depends upon this delta. That means the RMS of roughness and zeta, both depends upon material. For different material, this value will be different. So as I explained to you earlier regarding screening, that means for here, as I explained regarding screening, so when one electron is interact with this heavy ions or positive ions or an impurity, so there is a chance that the other electron present surrounding to this, they may be screened. So that screening phenomena it depends upon the material. That means the dielectric constant of the material. For different material, that screening is different. So as already I explained you regarding this, the in a quantum wave, as energy is confined, so that energy and wave function is expressed in this. So by using Fermi-Golden rule, we can obtain the transition probability, which is given by this. That W, the transition probability, which is 2 pi by x cross b n u square delta of this. So it make a transition from k position to k prime. That the final state is k plus q. So this b, which is the scattering potential. So the transition matrix element b, that Vnm, which is equal to 1 by a is psi m star j, which is equal to I k prime rho v of r psi m. So that can be expressed as in terms of this b of zq. This b of zq, which is equal to the Fourier transform of this v of r. So that Fourier transform that is called 2D Fourier transform of the scattering potential Vr is v of r e to the power I q rho into t rho. So that rho is equal to that k dot r. So here that q is equal to k prime minus k, that is the electron momentum transfer in the plane parallel to the interface. So in presence of other electron, the interaction between an electron and ionized impurity is strongly modified. That leads to screening. So screening of the ionized impurity potential, which we say it can express as a B effective Q, that gives after screening. So that screening, as I already told, for example, if you are moving, if you are riding or if you are walking on a road, a normal road, and if you are say you try to walk on water, then you will face the different force. So this is due to the nature of the material. So that dielectric material, dielectric constant has a very important role in this screening effect. So that screen scattering potential can be expressed in this summation over n prime n prime. So this into this potential. So this epsilon, which is equal to delta of nn prime, delta of mn prime. Nn prime means it transit from n to n prime, n to n prime, plus qs by q f of this into that zeta. So here in a multi-subband system, the effect of inter-subband coupling is twofold. It allows more scattering channels that leading to C01 and D01 in the expression, and it affects intra-subband scattering B00 for the dielectric screening matrix. So here this that F, which is known as the Coulomb form factor, it has specific notations, and this zeta, which is static electron density correlation function without electron-electron interaction. And for this screening, here there are models. We use the RPA, that is random phase approximation. We take the RPA model for calculation of this. Consider the screening effect. So here you can see, if you go for the further simplification, you will see depending upon the structure that you will get the screen scattering potential. Here, the screen scattering potential VNM, that is for impurity, is depends upon the doping concentration. Here I have shown for two different doping. As therefore, there is summation of this ND1 and first part plus second part. Specifically, it depends upon that dielectric constant as well as the P n prime QZI. What is that P n prime n prime? This is equal to summation, the integration over minus infinity to infinity psi n prime into e to the power minus 3 z minus zi. What does it mean? That means to design the mobility, to model the mobility, the scattering effect is important, and in scattering the tau is important. Tau means the transport time, mean average scattering time, and that tau is modeled by using the VT, and in VT we use the scattering potential, and if you take screening, that means we can change the scattering potential by modulating the wave function. See, there is overlapping of this psi n prime z. This is due to multi-subband that may be 0 or 1, psi 0, psi 1, like this. So due to this, so if you modulate the wave function, we can change the scattering potential. If you change the scattering potential, you can change the scattering type, tau. Then you can change the mobility. Then you can change the conductivity. So we chiefly focus on the primary issue, that how we can modulate this wave function inside the wave. If we modulate this, then we can modulate alternately the conductivity. So similarly, there is the screened Allais scattering potential, which chiefly depends upon this x and 1 minus x. That means it depends upon the Allais concentration as well as it depends upon the delta V. That means this Allais scattering potential height. So it also this into same thing. You can also modulate the Allais by modulating the wave function. They are overlapping of the wave function. This delta V, which is Allais scattering potential, and x is the Allais scattering fraction. Similarly, for interface roughness, here this kappa and delta, which are important because one is autocorrelation length and another is mean RMS value of the interface roughness, and also here it also depends upon that product. That means the wave function psi n prime into psi n prime. But here one thing is interface will get at z equal to zi. That means when you go a structure, so this was the substrate. So this is all gas, then you grow gas, gallium arsenide, then a all gas, then a gas. So specifically, it has shown from experiment that at all interface there will be not interface roughness scattering. Only if you are moving from the substrate, the first interface and the third, there are four interfaces. I1, this is I2, I3, I4 interface. But I1 and I3, they will contribute for the interface roughness scattering. So this is all about the basic mathematical description or basic theory how we can model mobility. So right now we will analyze some of our result that we have worked in. So as you know from day one, I have shown here. So in a quantum wave, this coupling, you split energy by coupling and confinement effect. So this is a single quantum wave. When you add additional barrier, then you can get a double quantum wave. And this double quantum wave, it has very significant issue, or it has very important impact on mobility. So you see, this is a single quantum wave. The left one, which is only a single quantum wave, there is no doping. This is a barrier, all gas. This is gas. This is all gas. Now the wave function E0 and E1, where this E0 is symmetric, E1 is antisymmetric. Now we can change. How we can change? Suppose as we go for the modulation doping. So when you make a modulation doping, that means the barrier take a spacer. This one is the spacer. S is for spacer. D for doping concentration. W for channel width or quantum wave width. So this is a single quantum wave. So when you dope from both sides, the barrier, let the doping is equal. If the doping is equal as per the Morphet concept, so there will be band bending. Thus, this band bending. So here this band bending is due to the summation of the kinetic energy plus electrostatic potential energy. So due to this band bending, now there is a V shape here at both the interface, and the each ray U1 accordingly change, and it also changes the wave function. So you see what is the nature of the wave function. Here it is symmetric, now it is symmetric, but this psi zero nature is changed. So you can also modulate this if you let you dope differently. This side is a substrate and this side is surface side. So if you also dope differently, that is the asymmetric doping. So due to the asymmetric doping, your energy level also shifts, and accordingly the wave function that can also modulate. So same thing, the another technique you can also modulate this. Suppose you dope only one side in the substrate. There is no doping in the right side of the barrier. So if you dope only in the left side, then you see the wave function psi 0 and psi 1 is lower than psi 0, psi 1. They are now present only in the left barrier, close to the interface of the left barrier and well. So it can change the property of the mobility. So these are the different technique by these are different structure through which you can modulate the wave function nature, which are the deciding factor for mobility. So now, when you apply field, as you know, this field is 0. When you apply field, the additional potential is added. What is that? EFZ. E is negative because we are taking conduction band. A charge is negative. So, when you apply field in this direction, that means from substrate to surface, then the potential will tilt upside. This field is tilt upside. So as it tilt upside, accordingly, see here, the below Fermi level, when there is no field, there are two levels occupied. Now when you apply field, the potential tilts, accordingly energy level change. Now below Fermi level, there is only single subband occupancy. So here, when F equal to 0, there are multi subband occupancy, whereas when you apply field at a specific field, that changes, it became a single level. So there will be intra subband occupancy. So that is a very important fact, important technique to modulate the mobility. So here, in one of our paper, that we take a single quantum wave. So as already I have shown you. So when F equal to 0, now this is the wave function, symmetric and antisymmetric. Now here we apply a field, and here this field is negative. That means we apply in the opposite to the z direction from towards the surface. As it is opposite, so the potential tilts downwards. So now when you apply field, now instead of this symmetric and antisymmetric, all the wave function, they are totally shifted towards the right side of the interface. As it is totally shifted towards the right side, that means when you are calculating the mobility, now the electron is in this barrier, in the left barrier. Now the position, the distance between the electron is not here, the positive ions, because we dope in the barrier. So the distance between the positive ions and the electron, now the wave function gives you idea about the distribution of electron. That means now the electron is distributed in this region. So now the distance increases because there is positive ions. Now the electron is distributed at this edge. So the distance increases. As the distance increases, R increases. As R increases, the Coulombic force F decreases. So the ionized impurity scattering can be reduced. It can improve the mobility. So this is in another paper that JAG. So here, instead of double side doping, we take a single side doping, and if here side is dope, double side dope, So no doubt the Coulomb scattering from left barrier, it can be reduced here. But what about the this right side? Because also there are doping in the right side. So there are positive ions. The dopants are in the right side. And now the distance between these dopants to this electron, now it is very close. So as it is very close, it can lead to reduce the mobility. So to solve this problem, instead of double side, we dope in a single side. As you dope in a single side, now when you apply field, now the electrons shift to the right side of the barrier. Now, however, there is no doping, so there are no positive ions, only the ions lies here. Now the distance is more, so it is improves the mobility very rapidly. So you can see this. These are the parameters which we are used. Normally we take the material gas or gas, and also we have did some work on gas in gas. So these are the material that are used here. So see one of these in result. So that means going very interesting results we achieve that the mobility behavior is non-linear. That means up to a specific field, there are single subband, then double subband occupied because we are increasing field. So energy changes, double subband occupied, and it continue up to a certain field. Then again there is single subband. So as there is single subband, during double subband occupancy, there is oscillatory behavior of the mobility. And that oscillatory behavior arises due to the Fermi wave function, EF0 and EF1. As it is like a cups like shape because EF0 means EF minus E0, EF minus E1. So as F increases, the EF0, EF1 that behaves like the cusp shape, CUSP cusp shape, and that leads to this oscillatory behavior. That mobility can be explained in terms of the intra-subband mobility. This is a mobility due to the lower ion's total mobility. This one is impurity. This one due to alloy, and the last one is due. This middle one is due to IR, and last one is due to alloy. And that can be explained in terms of the that inter-subband mobility, that is because mu II is due to mu 0 II plus mu 1 II. That means in the lowest orbit, in the lowest subband, you get mobility mu 0 II. In the first orbit, first subband, you will get mu 1 II. And jointly by the mathematical formulation that I have shown you, you will get the total mobility. And this mobility behavior can be explained in terms of the scattering parameters, BCD parameters. So as I already explained, the BCD parameter will show you the behavior of the mobility. So similarly, when you in here we take a specific doping concentration, that is 2 into 10 to the 8 in the left side. Now if you see, if you increase the doping concentration, that behavior nature changes. So you can see for NS equal to 1, this one, as NS increases, now the oscillatory behavior is more pronounced. And that oscillatory behavior will lead to very prominent device applications. So similarly, you can modulate this behavior of mobility by changing the oil width. Here, in this case, the oil width is 400. Now, if you increase the oil width, see this last one is 500. As you increase the oil width, the mobility also increases. Similarly, we can take a parabolic quantum oil structure. Parabolic in the sense instead of square, now because in square quantum oil, here this is 0, the potential is 0. But now you take the potential in the oil as in this form, half kz square, where k is 8 Vp by W square. Vp is the potential height, the parabolic height. So as x, the alloy concentration changes here, this Vx, which is obtained by this V, which is obtained by this band offset with the gas. So if you change x, you can obtain a parabolic nature of the oil. So when x equal to 0, it is square. If x equal to 1, this is the parabolic. And as x increases, the parabolic nature is more enhanced. So finally, there is a barrier Now inside the oil it is parabolic. So when there is parabolic, we see what will happen. Now this is the parabolic structure potential. Now this is due to ionized impurity. This one is due to ionized impurity. Now when you add, because the total potential is the structural potential plus Hartree potential. This is the Hartree potential. When you add, it will looks like a flat. As it looks like flat, that means instead of the carrier opening at the edge, now the carrier will move to the center. As the carrier will move to the center, at the edge, it will behave like a two-dimensional. However, at this center, it will behave like a three-dimensional electron gas nature, and it can improve mobility. So this is the, that means here we take a single parabola. So in a single parabola, we are not getting any oscillatory behavior. Only as field increases, the mobility, there is double subband, so the mobility seems to be very constant, and at transition, that means there is a, now the Fermi level goes down, there is only single subband occupied, mobility suddenly enhanced, then it decreases with the field. So this is a coupled quantum oil structure. That means when both the oil will be separated by central barrier. So here also we can take a different concept, like you dope in the left barrier only, or you can dope both sides of the barrier symmetrically, or you can dope either in the, towards the substrate or towards the surface. So accordingly, your wave function distribution will be modulated. So this is a double parabola that I explained, single parabola. Similarly, you can, if you take a double parabola, now this red one will be due to parabolic plus ionic. That means the combination of Hartree. So same thing in a double parabola. If you apply field, it will fields that that can change the occupation of number of states. So here in one of our paper, that means we dope equally on the both side and we apply field. So the, now the carrier, that means the electron totally shift to the right side of the oil, and it modulate the mobility very nicely. So here either you can apply field along the growth direction or opposite to the growth direction that I have shown. If you apply along the growth direction, that means from the substrate side, the potential will move up to the substrate, towards the substrate. And if you apply the field in the negative, that means from the surface side, then your surface side, that means the right side, left side will move up. So the potential, whether it move up or down, that depends upon the direction of electric field. So this is in one of our result I have shown, explained. So here, if you see, this is a double quantum wave. We dope only at the left barrier, and in the left barrier, and we got the mobility. You see the mobility, if you compare with a single quantum wave, this is a single quantum wave and this is a double quantum wave. Now in a double quantum wave, the oscillatory behavior of the mobility is more prominent. And this is due to the confinement and coupling effect. Because in a double quantum wave, as there is the central barrier that can reach the coupling effect, which boost this mobility. That means due to the coupling effect, that EF0 and EF1 became more sharp. They come very close to each other. That leads to more oscillation. This is another comparison for a square and a parabolic in a double quantum wave. So obviously in a double quantum wave, if it is square, you can get a high mobility. But when there are two subbands occupied in parabolic, you will get high mobility during double subband occupancy. So this is one where we saw the inverted dope structure and non-inverted. That means we dope in one case we apply field from negative side, in another case we apply positive side. Then when you apply this different direction, then the II and eddy scattering, they remain same because they are symmetric potential. But the IR will be changed because IR is asymmetric. We take only the I1 and I3 that I have shown. which is taken from the left side of the from the substrate. So due to the IR, which is asymmetric nature, very interesting phenomena arises that I will show you. So this is in a recent one of our paper that we modulate, we take a double parabolic quantum structure. We take here, we dope the left barrier with a, sorry, the right barrier, the barrier, surface barrier with a 1 into 10^18, and we change the doping concentration in the substrate side, and we apply different field. That means here field is fixed. So when as field increases, that means when we apply high field, as MD increases, there is an improvement in mobility. As including this, the property, the nature of the mobility also changes. So this is due to the asymmetric nature of doping, and we included the field effect. So same manner, we can also modulate this. That means instead of taking symmetric oil, you take one oil less, another oil large. If you take a asymmetric oil, you can also modulate the wave function. You can see here. So here, this wave function is totally modulated, and here doping is same on both sides, but the oil is different. That means the oil, we take a different oil, and accordingly we modulate the wave function. So you can see here. So when the W1 plus W2 is 300, it is kept fixed. That means we take this W1, W2 fixed. That means as we change W1, so accordingly we keep W2. For example, when W1 is 200, then W2 is 200. So and we dope only in the left barrier, this side, ND1, there is bending, and there is no bending, no doping in the right side, that is ND2 equal to 0, and it also gives very oscillatory behavior nature. And here, this nature is more prominent in case of your this. That means the oscillatory behavior arises in the IR as well as in the impurity. However, so you can see this mobility is governed by impurity and IR. So as B increases, as I explained to you, the central barrier, it has very prominent effect. As B increases, then that oscillatory behavior is very fast, very rising as compared to the lower barrier route. So similarly, we can also make that asymmetric in terms of doping. See, there are doping, symmetric doping here. In left side, only you change a slight doping. The psi 0 is totally in the left side, and psi 1 is totally in the right side. That means overlapping is very negligible. If overlapping is very negligible, then the scattering will be very less, because the scattering potential depends upon the overlapping of the wave functions. So in this manner, we also see here. So that means when we take ND1 vary and ND2 fix, as ND1 varies, then so there is a resonance. That means when ND1 match with ND2, when the structure becomes symmetric, there is maximum overlapping. So as there is maximum overlapping, so the scattering will be maximum, so mobility will be minimum. So at ND1 equal to ND2, there is a resonance, and there is a sharp peak in the mobility. And specifically, already I told you, the impurity and allied error, they are symmetric. That dip is due to the interface roughness. Here also, as B increases, that dip gradually increases. If you see the last one, the top one, B equal to 80, where you get the maximum dip. And you can see here also, this is due to this energy level. When B is equal to 80, now you see here it is taken for 60. When it is 60, now the gap at the resonance point, there this is very close. As they are very close, that makes the dip. So similarly, here you can get in gas structure this oscillatory behavior. Okay, actually the time, just I will take 3-4 minutes. So here you can also get this is also due to the doping asymmetry. Now in another way, we can also make that asymmetry in the structure. That is, you take a hybrid structure. That means instead of taking two square or two parabola, you take a square oil in one side and a parabola oil in another side. So even though all the parameters are same, that is symmetric, but the structure potential is asymmetric, and that leads to the asymmetric distribution of the wave functions, and that modulate the mobility. So here I have shown you. So at you can see this case C case where resonance occur. That means we take ND1 equal to 1, but ND2 equal to 2.6. That means normally if the structure is symmetric, the resonance should occur at ND1 equal to ND2. But here, as we initially made the structure asymmetric, we dope differently and we make the resonance. And at the resonance, there will be drop in mobility. It will give you asymmetric, that is oscillatory nature. You can see here. So this oscillatory behavior. So here there is a single subband occupancy. So as ND2 increases, mobility increases. But you can see now this is in the double subband occupancy. So as the structure is asymmetric, when we make ND2 increases at ND2 equal to around 2.5, now there is a dip, the drop in mobility, and that drop is sharp at a larger width of barrier. So this is, you can see also here, when B equal to 60, now this EF0, EF1, they are very close as compared to B equal to 20. So there are other structures that you can also modulate wave function. That means simply you change, instead of a square, you can also take a V shape. So simply we know the potential, which is obtained this expression 0.693x plus for a parabolic. But if you take this, you see this structure expression, which is V into Z mode minus V plus W by 2 to the power n inside the OL, where this W is the OL width, V is the barrier width, Z is the position of the growth. So this V is the electron. Here we say this V height of the OL. So now if you change that n in the modulus factor, if you change n, then you can change the structure. When n equal to 1, it became a V shape. When n equal to 2, it became a parabolic. And when n equal to 3, it became a cubic. And if you go on increasing n at a limit when n tends to infinity, now that structure became a square structure. So as you can modulate the structure, you can modulate the wave function. Accordingly, you can modulate the mobility. You see one of our in this paper. So here we change this symmetry, and we got the asymmetry in mobility. That during double subband occupancy, there is oscillatory nature, and this nature you can achieve due to this at this interaction point. Okay, so this is all about how we can modulate wave function, that modulate tau, that can modulate the wave function that can modulate the scattering potential, which also modulate the tau, and that can modulate the mobility, which can modulate your current density in the device. So overall, we first here discuss regarding nonlinearity in mobility, which is obtained by suitable choice of structure parameter and also by applying electric field in a double subband occupancy. Through we can modulate it, that nonlinearity through change in the distribution of subband wave function and energy levels, and inter-subband effects near change in the occupation of subbands, and there is a drastic change in the subband wave functions near the resonance of subband states. So that oscillatory nature we can obtain, or we can of mu is more in inverted dope as compared to that of surface dope structure, and this is due to the asymmetric nature of higher scattering potential. That means we can make the structure asymmetric either applying electric field, or we can change the OL width, or we can that means to change the doping concentration on both sides, or we can make that means the structure itself asymmetric, one square, one parabolic. So this is all about. So here these are actually, Professor Tina Sau, who is now at NIST, is my mentor and head of our group, research group. Professor Ajit Panda sir, I am his, I did my postdoc that NPDF, National Postdoc Fellowship, and the Sangeeta Palo, which she is our collaborator. She is also student of Professor Tina Sau. She also did that NPDF, National Postdoc Fellow, under this Ajit Panda sir. And right now, there is Mr. Ramchandra Swain, Mr. Ajit Sahoo, and Mr. Asutosh Patnaik. They are the scholars. They are doing research under my guidance. So thank you all. Thank you for your patience, and I will be happy if there will be any questions. Thank you.
Yes, thank you, Dr. Sahoo. So, if you have any question, please ask to Dr. Sahoo. Please don't do the annotate when speakers are painting. Please don't do the annotate. I can disclose the names, but I don't want to disclose the names. Some of you are doing this some childish behavior. Please don't do that. I can see the name, your name actually. I can see the name, and sometimes I send the private message to them also. Well, if you have any question, please ask to Dr. Sahoo.
Can I ask?
Yes.
Yes, use your short question because we are running late.
Yes, yes. Sir, it was very nice presentation starting from the, very fast day to this day. It's a very nice and great presentations, and the lectures are series of the lectures. I would like to request the coordinator if you kindly send all the videos. It will be very helpful for us to in future.
Yeah, we'll upload all the videos in the group.
Okay. So just my one short
Yes,
question
yes.
is here. That is, if is there any possibility that we can hybrid your quantum well structure? There is a parabolic quantum well structure with the inverted quantum well structure.
That means you want to know in parabolic.
With
Can we?
inverted quantum well.
Yeah, inverted quantum well. In one of our paper, we also made that inverted in the sense, actually in our research activity, we are only analyzing this mobility by modulating the structure. So inverted means when we apply the field opposite to the actually as the growth direction is from the substrate. We normally grow from substrate to surface. So if we apply a field from the substrate side, then we say it is a normal quantum wave. And if we apply negative to the z direction, we say it is inverted structure. So in one of our paper in AIP in 2014, American AIP advances, we did that inverted structure and we obtain the modulation of that mobility. It can possible.
Okay, sir. Thank you. Thank you.
Okay, thank you very much. Specifically, I wish that means express my gratitude to Devanjan sir because his interaction and also Madhusudan and Panda sir, your interaction make me very interactive in this lecture series. And I hope that means all should ask questions and all should be interactive so that the session will be more vibrant.
Yes, all right.
Thank you, sir. Thank you, sir.
So, any other participant have any questions?
Hello, sir.
Yes,
I'm Dr. Geeta. Actually, you had given a very detailed presentations over the past 3 days, so it was really helpful for us to understand from the basics. So since we at our place here, we are working on some materials like chalcogenides for thermoelectric applications, and these chalcogenides, as we know, that they are having very low lattice thermal conductivity. So but still we could see that the ZT, the figure of merit of these materials, are not very much competitive. And there have been many other ways to reduce the lattice conductivity or phonon conductivity. So how would you think in your way, like making a super lattices, whether it would be beneficial for reducing the lattice thermal conductivity? What are the ways?
Yes, actually, but you asked, actually, I am not the exact concern to reply, but as per my knowledge, so that means not only the mobility, we can also modulate other property like thermal conductivity, and that means this is in some of the paper in nanotechnology, specifically journal. So we have seen, but as per superlatives, this gas, gas or gallium nitride, these material are very prominent one. So I don't know whether that will helpful, but if we go in detail in literature, then I can reply your actually
Right, sir.
query.
Okay, sir.
Yeah,
Maybe
because I
sometime
have
later.
actually not in depth knowledge on that chalcolite material, so I think I will not comment. So
Yeah.
that
Yeah, because this is a very great technological challenge what we
yeah.
are facing, at least, the people who are working in energy harvesting. So there is no other material other than bismuth telluride which has been, replaced the market. So the very intrinsic problem, what we understood is engineering the thermal conductivity part.
Conductivity.
Yes, yes, sir. Okay, sir. No problem. Thank you very much, sir.
Thank you. Thank you.
Yeah.
Yeah. Is there any other questions? We can take the last question, if any.
Sir, if there is any no other question, can I ask last question?
Yeah.
Yeah, definitely,
Yes.
definitely.
Yes. Yes.
So that is just very basic things. All we have already understand whatever the things we have known from Dr. Sahoo. But the thing is that I want to enlighten from you that why the wave function is evanescent at the quantum at the side of the quantum oil, and it is higher at the middle of the quantum oil. Can you enlighten on this fact? I mean, we want to know your views on
Okay.
this.
So just to clarify your queries, so let me show this figure. So that,
It's a very basic thing,
yeah,
but
yeah,
you
yeah,
have,
yeah. Very, very basic. Yeah. So if you go anything, so
because the first undergrad students are
this
asked
one.
this thing.
Okay.
Yes, yes.
So this one. So
Why
if
the
you see,
wave function is evanescent
yeah,
at the side
yeah,
of the side wall
yeah,
of the
side.
one.
So that means here in a quantum well, actually we make a modulation looping. That means both sides of the well. As we modulate it, that means if you modulate only take a Hemp or MOSFET structure only in one side, so there is a V shape in one side. But here we take modulation on both sides. As a result, it can take V shape on both sides of this barrier.
No, sir. No, sir. I am talking
In this figure.
about this one. That
Oh, this one.
the left one. Yes,
Left one.
yes, yes. Here you can see that the wave function is of the electron is
Symmetry.
evanescent at the end. Yes. So why that
This
is sine wave, not a cos wave?
that sine wave. Okay.
Yes.
That means
That
this
is,
one, psi one. You want to
yes,
know the psi
whatever
one,
you
sine.
can understand, whatever you
So
can.
this is
Why
the
not
simple.
cos wave?
Okay. So this is the simple. That means mathematics that if you solve in the Schrödinger's equation. So if you solve, so there is a chance that because there is some. You can take either sine function or cosine function during the solution of this. So probably as it is, that means sine. So you can say we are normally using the boundary condition. That means at boundary, this should be zero because we always try to make it ideal for a ideal situation, that is which obtained at infinity barrier. So as to make it ideal, that means it should be zero at the boundary. So that's why we consider it as a sine wave.
Thank you, sir. Thank you very much.
Well, thank you. I think there are no more questions. I have already shared the test link in your chat box. Please answer the chat, give the test. So this is the last talk by Dr. Sahoo. So that's why I like to request Dr. Devanjan Acharya to give vote of thanks to Dr. Sahoo. Dr. Acharya, please.
Yes, Thank you, sir. It's my privilege to give the vote of thanks to the pioneer professor like Dr. Sahoo, and he has done very tremendous efforts on this basic physics, physical structure, I mean quantum world structure. I have also gone through his papers. It's a very he has great research effort on this topic. And from the start, the beginning, I have attended most of the part of his talk. That is, I feel very excited. That is all the electronics. I am from the electronics background, and not only the electronics and right now it is a quantum computing era. So all the things are basically depends. Basically it is depends on the basic physics, the understanding from the basic physics. And he has starting from the heavy hole to light hole, then the intra-subband, and then hybrid quantum structure. Here I mentioned and explained all these things from starting from the undergraduate level understanding to the research level understanding, even from the postdoc level understanding. So it's a very nice presentation, and we have also nice interactive session. I get some clarification about the different basic understanding also. So I would look forward. I look forward to touch him within future. And it's a very nice presentation. Thank you very much. Thank you once again, Dr. Panda, to give me this opportunity to give me a photo. Thank you all.
Thank you for your kind words. Thank you, and
Thank
also
you all.
for all